Okay, so welcome back to another video. Here's a little definite integral where the base is a negative number. So we have the definite integral from 0 to 1 of -1 to the power ln of x dx. Sadly, it is not the Euler's constant e, otherwise it would have been e ln of x and we would have just had x. Would have been an easy definite integral to calculate and we would have just called that a day. But here this is a little bit different. So you might be thinking, how's that possible to integrate? Because it may look like there's no possible way to get this into some form of like elementary functions. Well, if you want to think a little bit outside the box, we can actually go back into the world of complex numbers and do some complex integration. So I think for anybody that can tell what's going to happen here, they're going to be involving Euler's identity, which says that e to the power I times pi, add this with 1 is equal to 0, or if you want to subtract the 1 and set the equality equal to each other, that's still the same way you can do that, then we can actually make that substitution and put that in, and then it actually follows with the rest of the results that there's actually two results that this can be very important to use, and I'll actually prove both of those results. However, one of the results is, well, if we start with that, proving that one result, then the other one is actually in a similar procedure that follows as well. So it's going to be a short proof, in other words. But everything just follows up from there using Euler's formula, and yeah, it's all about complex integration. So we're going into a different number system instead of doing this with real numbers. So let's actually just jump right in. So I mentioned that we use Euler's identity that says e to the power I times pi is equal to -1. But actually, let's go a little bit into the extension and consider that if we look at this from, the complex plane, that if we look at this from, the Euler's formula, we have to consider the periodicity. So the value of e to the power I times pi, it can equal -1 in certain places. So we actually have to set this little extension and say that this appears for every 2k plus 1. And that says that k can be any integer. So this is actually very important to see that you can't just do this with just one value. This happens at every time that, if we look at this from the unit circle, that this appears at every 2k plus 1, that is going to equal -1 with the extension of Euler's formula. So with this, now we can actually make that proper substitution, and here we go back to the original integral. So -1 to the power ln of x, then dx. Simply it's just 0 to 1 of e to the power I times pi, then 2k plus 1, then to the power ln of x dx. Then simply we know that just with properties of exponents, we can actually just multiply and distribute through here. It's multiplication, and so now we have this integral we have to calculate. E to the power I times 2k plus 1, then multiplied by pi, then ln of x multiplied by dx. And so from here, now let's actually use that whole definition of Euler's formula, which says that e to the power I times x equal to cosine of x plus I times sine of x. And here we're going to actually have an input of 2k plus 1, and then multiply by ln of x. So now let's actually put that in. So let me actually make this little notion and say that I to the power 2k plus 1 times pi ln of x, this is going to equal to cosine of 2k plus 1 multiplied by pi, then times ln of x, then add this with I times sine of same input, 2k plus 1, then pi, and then ln of x. And so here, that will mean that we're basically taking this entire integral, and then jumping a step a little further, we can actually apply some linearity and then put this as a sum of definite integrals. So now our new integral, the new expression, can be rewritten as follows. So we have from 0 to 1 of cosine of 2k plus 1, then times pi ln of x dx. Then add this with the imaginary units, so I, and then multiply by, simply because I is just imaginary number in this sense, so we can actually move that outside the integral. I times sine of the same input, 2k plus 1, then times pi, then multiply by ln of x, and then dx. Now you might be thinking, how can we actually perform this little calculation of both these integrals? Because it doesn't look like this could be easily, we can easily integrate this. Well, it's okay because we, of course, with complex integration, we could still apply some of the stuff we do in, regular integration, real numbers, so we can actually do some use substitution. So let's actually suppose that if we let this variable, we're gonna call this negative t. So let negative t equals ln of x, whatever variable we want to choose. This is a little bit easier that way, that eventually when we actually convert this to the new bounds, then everything just comes out nicely. We use negative t equals ln of x, then we solve for x, so just take the e base both sides, so x is equal to e to the negative t. Differentiate both sides, so dx is equal to negative e to the negative t dt. Okay, and so from here now, let's actually just plug all this back in for the new substitution, just like so. And so we have our new bounds as well, so let's first start off one thing at a time. So we plug in 0 for x, then that sees that t is going to have to be infinity. And if we plug in 1, so the upper bound is going to have to be 0. Then we plug all this back in, so let's see, we have cosine of 2k plus 1, then times pi. Then we just fill in the, what we said, ln of x, which is equal to negative t, so negative t. Then we multiply this with our new differential for dx, and that substitution, converting it into the rule of t, so negative e to the negative t, then multiply dt. Then next, we're going to have, now do the same thing, so plus I, and then, so this is going to be the same bounds again, it just follows by the same thing, so infinity, 0, then sine of 2k plus 1 multiplied by pi, plug in negative t in, and multiply with the dx differential, so negative e to the negative t, then dt. Okay, so we can actually simplify some stuff out. So let's actually do that. So first, we can actually just interchange the bounds, so that would also have to mean that that becomes negative. That's okay, so the negative and the negatives cancel, so it'll still be positive. And don't forget, we have a negative t in the input of cosine, but cosine's an even function, so that negative will just disappear and everything will still be positive. So infinity and 0, and then cosine of 2k plus 1, then multiply by pi times t, then multiply with e to the negative t dt. And now let's actually move on to the this integral over here. So let's see, so first off, same thing, just like before, follows, you interchange the bounds, that becomes negative, then negatives cancel. However, sine is an odd function with this negative input over here, so we'll have to factor out the negative. And so we can actually change that sign, so this could be a minus I, then times this same integral, same integrand as follows, except just replace cosine with sine. So sine of 2k plus 1 multiply by pi times t, and then multiply by e to the negative t dt. And so let's actually, now, these are the two results that we're going to be using. I'm going to prove both of them, but it just follows that after proving the first result, it actually, the second result's going to follow that same procedure as well. So here are the two results we're going to be using. So let me first put this down. Result. First, the first integral we're going to be using, so this is an improper integral. So 0 to infinity of e to the power negative a times x, then times cosine of b times x is dx is going to equal a divided by a squared plus b squared. A squared and b squared can be any number of your choice. And then the other one is same integral, but instead this is going to be sine. So e to the negative ax times sine of bx is going to equal instead b divided by a squared plus b squared. Okay, so we're going to prove this result over here. So you might be thinking that we can actually do integration by parts. Well, yes you can, but when it comes to the point where you have to evaluate the bounds from 0 to infinity, and you can actually show all this work and see where I'm coming from with this, but if you were to unplug infinity, this is very interesting to see that when you take the limit of some for infinity, for example, in this situation, of a trigonometric function, notice that both sine and cosine are actually bounded from between 1 to negative 1. And if you were to take that like all the way approach towards infinity, it's actually undefined. So that actually leaves a little bit of a discretion, and you can't just really say that it's going to equal 0 for the whole thing. Now, I'm not sure specifically myself. I know I tried all this work. Now I'm trying to think that, I was thinking at the time thinking that if you're going to apply L'Hopital's rule, that might work, but it doesn't in that situation. But instead, we're actually going to use another technique, and it's actually just by doing the same thing before, just replace the cosine and sine with using Euler's formula. And if you think about this, we can actually take the real and the imaginary parts to get these similar results. So first, we're gonna so even if we start up with this first result, it's actually gonna follow for the same. So we're gonna replace, so first I'm gonna put this as the real part, since the real associated with Euler's formula is with cosine and imaginary is with sine. So I'm gonna say the real of this integral 0 to infinity of e to the power negative ax, then replace with Euler's formula. So I replace this with I and then times bx for that input, dx. Okay, and so from here, we could actually use the, so I'm gonna just disregard the real part for notation for a sec. And so we have 0 to infinity of e to the negative ax, and then add this with I times bx dx. Then we can actually factor this out. So 0 to infinity for the exponent. So we have negative a, and then times, or rather subtract I times b, then x dx. Simply, we can actually do some, this is use substitution. This is very simple to see that we have negative e to the negative a, then minus I times b, then x, then divided by, this will be a minus I times b. Then evaluate this from 0 to infinity. And then simply we can see that over here, that if we plug infinity, this is going to be 0. And if we plug 0, this is actually going to be 1. And so we have 1 divided by a minus I times b, but let's actually fix that and put this in forms of, multiply by its conjugate. So if I do a plus ib, and then put down the multiply from the denominator, so that'll become an a times, or a squared divided a squared plus b squared on the denominator, and so that'll leave us with a plus I times b. So simply enough, if we take the real part, which is actually exactly this follows, then we actually get this result is a divided by a squared plus b squared. And if we were to take the imaginary part, it actually follows from the same thing for that's associated with sine, and we actually get b divided by a squared plus b squared. And so therefore, we this actually just completes everything. So let me actually put it like this. So you know what? I don't actually really need to say that. You know where I'm coming from. The real is going to associate with a divided by a squared plus b squared. We take the imaginary that's associated with sine, that's going to be b divided by a squared plus b squared. So it actually completes all that. And so now using these results, so now we can actually do a little bit of substituting those inputs. So first, our first integral, 0 to infinity of cosine of 2k plus 1, and multiplied by pi times t, then e to the negative t dt. If you put in the right inputs, then we're going to get that first is that this is going to equal 1 divided by 1 plus 2k plus 1 quantity square, and then multiplied by pi square. And then the other result follows that if we take this from the same thing, it's like sine. So sine of 2k plus 1 pi t, and e to the negative t dt is going to equal to 2k plus 1 times pi divided by that same denominator over here. So 1 times, or 1 plus 2k plus 1 quantity squared, then times pi squared. And so with that, we actually just substitute all this back in. And so therefore we actually just finished the, we finished calculating this little interesting integral. So therefore, the final answer is that the integral from, let me see, -1 to the power ln of x dx from 1 to 0 is going to indeed equal 1 divided by 1 plus 2k plus 1 square pi square. Then now we have that minus, so minus I, and then times 2k plus 1, then times pi, and then divided by that same denominator, 1 plus 2k plus 1 quantity square, and then times pi square. And so just like that, we have finished calculating our little integral. And yep, sometimes with negative bases, because usually with bases, it's easier to deal this with, variables, but because that not only we're dealing with, a real number, but it's also a negative. So you have to, in other words, be careful of like how to integrate this. You might have to, in other words, you got to be a little creative and do a little bit of substitution instead of having to deal with this like in integrating in terms of elementary function. You might have to deal this with like another number system, just like what we did in the complex world. So yeah, that's pretty cool if you ask me.